Good afternoon or good evening, everybody. Let's go for the first talk. So from Professor Nilesh Vasa, who is working as a professor in Indian Institute of Technology of Madras, and he will present us a laser-induced breakdown spectroscopy technique for online elemental analysis application and its recent advances. So, give you the floor, Professor.
Good afternoon to everyone. Okay, I'm Vasa from Indian Institute of Technology, Madras, Chennai, India. And our team, we work in the area of laser-assisted sensing and for various applications. Of course, in this presentation, I am going to talk about laser-induced breakdown spectroscopy technique for online elemental analysis application and recent advances. The most of the input which I'm going to talk here in this presentation, right, is based on our research work in our laboratory here at IIT Madras. We'll go to the next slide. So, first, what's about laser-induced breakdown spectroscopy, LIBS, and why are we considering LIBS, right? Laser-induced breakdown spectroscopy applications as such. So, this LIBS technique is not new. It's after the first laser came out, and then within few years when neodymium YAG laser also came, so lots of research started working towards how can we make use of high energy laser source in order to realize elemental analysis. So basically the process is based on the ablation. So the high energy power lasers can be used to ablate the material, and then let's try to see how it can help us to analyze the material is the idea with which the LIBS started coming into picture. And the advantage and why do we go with the LIBS technique, right, and how why it became so popular. And you can see that in last 15-20 years the progress has been tremendous. Now there are some instruments which we are trying to implement in terms of online and real time application, etc. So I'm going to discuss on this aspects. So basically lasers, laser-induced breakdown spectroscopy technique, LIBS, is very useful elemental analysis tool because it offers real-time or online analysis of elements, essentially, any material can be ablated and we will be able to analyze it. And it's a non-destructive to certain extent, I should say, because at the micron level material removal is possible, and hence by using such micron level material removal approach, we are not disturbing the whole structure or whole measurements aspects. We are just trying to capture a very small amount of information from the ablation. So optical access to the specimen is only required, and possibility of remote sensing is possible. No minimal sample preparation. We can use it for solid, liquid, gas samples, and hence it has wide range of applications. Okay, it's applicable in industries, archaeology, analysis, in situ or medical applications, forensic, remote sensing, etc. Of course, Mars rover is also one such example where laser has been used for analysis purpose. Now, in such applications, before we go into details, for those who are new to this approach, the technique is basically it utilizes a pulsed nanosecond pulsed laser. We can use even a short pulse laser. However, traditionally, right, pulse nanosecond laser is used, and the laser beam is being used in order to heat the material, and then correspondingly the temperature increases, and of course thermionic emissions, electron emissions, etc. Improves the absorption of this laser further, and we end up with further heating of the material, resulting into melt, then subsequently vaporization, and further increase in temperature goes up to few thousands of degree Kelvin, few thousands of degrees centigrade, or few thousands of Kelvin, 10 to 15 or 20,000 Kelvin easily, in a very small plasma plume, which is of the order of a few hundreds of micrometer or so. And then it when this plasma plume, which is very hot, when we see its optical emission from the very hot plasma plume in the initial stage, maybe of the order of few tens or hundreds of nanosecond from the point of time of ablation, what we will see is a very wide continuum along with some optical emission lines. Now this this broadband continuum is because of the lots of plasma induced electrons, excited electrons, which are when the plasma is getting cooled, and they emit certain line, so wavelength ranging from in the visible range, wide visible range. That's why we see a wide continuum. However, after maybe few tens or hundreds of nanoseconds, depending upon the type of laser ablation, what we see is the characteristic emissions of some of the elemental lines which are present in this material, and those specific emission lines are basically they represent the signature of these elements which are present in this material. Okay, so as a simple experimental setup, it involves laser, which may be a nanosecond pulse laser such as neodymium YAG, or even excimer laser, or short wavelength third harmonic or fourth harmonic generation of the neodymium YAG laser, etc. we can use. And then it also involves a spectrometer which collects the optical emissions, and we will show you that we also can involve a photomultiplier tube and ICCD systems in order to determine further details of this plasma plume which is being generated, and derive better information related to the elemental analysis. And first application which I will be considering is related to remote LIBS technique. Remote LIBS because we have used this approach for the LIBS approach with the distance of the order of few meters to 40 meters or so. So our idea was to develop a remote diagnostic condition monitoring technique adapting the LIBS technique. Why is it so, and for what application? So here I am just trying to show you that it's a wind turbine blades. You know that the wind turbine blades are of the order, means the height of this tower of the wind turbine blade system would be of the order of 100 to 150, 60 meters, and on the top there will be wind turbine blades which are of the order of again 50 to 40 to 60 meters or so. So the length of the wind turbine at the height is very high, and generally lightning will not get attached to this wind turbine blades because they are made from glass fiber reinforced plastics and vacuum molded. We do not expect its lightning to attach with it, being an insulator, right? However, with time, particularly in the coastal region, etc., when some pollutant layers such as salt, etc., gets deposited, we end up with deteriorating this insulation characteristic, and electrical integrity of this material gets degraded, and hence the lightning can attach to this wind turbine blade, damaging it to the extent that it gets broken, and then the replacement becomes so difficult. So can we capture this pollutant layer from the distance was the right idea that we embarked on. And first we started with small tabletop studies where we used reference target GFRP material, and then we deposited various concentrations of basically the salt deposition density was controlled on the surface, and then we were trying to see through what is the optical emission that we can capture. So here this plot shows one of the spectra of the spectral characteristics of the substrate material, GFRP material, and you can see that multiple such emission lines represent the characteristic of presentation of the material elements present in the substrate. However, when there is a salt deposit on that substrate, and if we try to see the laser plume and LIBS based on the LIBS study, we can easily find out that the sodium emission from the salt which is deposited becomes very, very prominent. And that prominent line, sodium emission lines, can be used for our elemental analysis purpose. In order to analyze the pollutant layer thickness. And we parallelly, we also studied electrical discharge studies in order to realize that really how the dielectric strength or the material characteristics are getting degraded from the electrical point of view because of the salt deposit, and with the various concentrations of the salt deposit, how this surface characteristics are getting deteriorated. Although I have not described the high voltage test results over here, but what we observed through optical emissions during this high voltage discharge also clearly showed even sodium emission lines, and that was matching with what we were trying to observe even with LIBS. The advantage with LIBS is we can do this study with remote place, from the remote distance, as compared to in the case of high voltage discharge studies, where we require a laboratory setup to conduct this experiments. And then we varied the salt deposit density concentrations, and corresponding to the concentrations, we were trying to capture the optical emission plasma persistence time. Depending upon the salt deposit concentration, the plasma persistence time was varying. Of course, there were some challenges in terms of the laser energy variation, which affects the LIBS characteristics. So we understood that we need a laser source which can be stable, which can provide input energy and the laser fluence of the order of few joule per centimeter square, but at the same time a stable laser with and the variation in the laser intensity critically affects the plasma emission time corresponding to the concentration of the salt deposit. We also verified that when we increase the laser fluence in order to ablate the material, and if it goes beyond the particular laser fluence, then what we observed was a very large variation in the salt deposit concentration, as you can see here. So the safe operating limits for laser ablation, and then observing this LIBS characteristics was found out to be, means it was estimated to be around 2 to 3 joule per centimeter square, which was good enough to obtain appropriate results. When we go beyond this, because of the laser energy induced plasma which is getting generated, used to absorb the incoming laser beam subsequently and affecting our measurements, etc. That was observed very clearly. And in order to do or carry out the results, the studies for long distance measurements, we used a laser beam, and then focusing it on the object, and then capturing the plasma emissions from the distance using a telescope system, using an aspheric mirror coupled with the translational mirror, flat mirror. So it's basically a Newtonian type telescope approach. But what modification we did here is the configuration was set in such a way that the laser beam which is captured, the plasma optical emission which is captured using this light source, can capture from varied distance. Depending upon the distance, this position of this optical fiber which will collect this light will accordingly be adjusted, and according to that, the optical efficiency, optical light collection efficiency can be improved in the spectrometer. So these studies were carried out using spectrometer studies, that is optical spectral studies, as well as temporal studies, simultaneous temporal studies of the sodium emission line, persistence lifetime, which was also captured. What we observed with the spectral studies is, as the distance increases, of course, the sodium intensity level also decreases because of the optical window which limits this collection efficiency, and hence up to 40 meter we would be able to collect with our approach. We were in position to collect the optical emissions and correspondingly measure the concentrations at different with salt deposit concentrations. So basically we could achieve this technique, remote sensing approach, using a photometric device developed and used in our experimental setup in order to collect the information from the wind turbine blade. So with this, I will try to give you another application which we extended it, our LIBS application, towards condition monitoring. Of course, this is the long-term goal. We started with studying aging of a transformer. So aging of transformer is very important, particularly, we know that the transformer is a very important part of the power system network, and the failure of such transformer results in a very large loss in terms of economic as well as in terms of inconvenience to the users. Now, the life of the transformer also depends upon the life of the insulation which we use. So the transformer mainly consists of a transformer oil and the solid insulating material such as press board. So the press board, which is known as oil, which is basically oil impregnated press board material, is under high stress. Not the mechanical stress, but thermal stress mainly, electrical stress, and some of the other corrosion effects, along with the mechanical small amount of mechanical stress. So the aging of this oil impregnated press board becomes a very important aspect. And how to study this process and how to realize that whether the contamination is getting into this type of press board material or not was the idea. So So we started, and of course, the reason behind this is when this oil impregnated pressboard becomes contaminated, basically what happens is the copper, which is the oil impregnated pressboard covers or surrounds the copper, right, wires, etc. And if the copper contamination comes into picture, it gets penetrated through this pressboard, and in terms of it produces some harmful effect. It adversely affects due to the localized arcs, right, as well as reduced current carrying capacity, etc. And that's where the premature failure of the transformer can result. So if we can detect any such copper contaminant on the surface of this pressboard, it may be helpful is the idea. And how to detect this? Can we use laser-induced breakdown spectroscopy for this? Is the point that we wanted to study. Basically, in order to see the characteristics of this copper diffusion, what we did is we added DBDS, which is nothing but the sulfur compounds, organic based sulfur compounds, and that sulfur compound interact with the copper material through this insulating material, and then the dissociated copper can diffuse into the insulating material, representing a type of aging characteristics. So we did such aging measurements with different such samples being treated under different temperatures for different working hours of those insulation materials. And what we could observe that, see, this is the LIBS spectra, typical LIBS spectra which was observed. And this is we can see that depending upon the aging right characteristics, so the virgin oil impressed oil, this impressed pressboard was having certain optical LIBS spectral lines, but with aged oil impregnated pressboard, we could see some of the important lines corresponding to the copper contamination. And we also observed this copper contamination time, the persistence lifetime corresponding to this such copper emission lines. And we could see that with the increase in the volume or the concentration of copper, right, and aging duration, we could see that the persistence lifetime also changed and increased. So that could be an equivalent measure of the aging characteristics is what we could observe. Of course, from the laboratory, from the research perspective, we also tried capturing in the vacuum ultraviolet region, right, and extreme ultraviolet region, the corresponding sulfur emissions, because we were expecting that when copper gets diffused and the DBDS will also release sulfur, and some copper sulfide or sulfur getting diffused through this impregnated pressboard can also indicate that how the diffusion process is progressing. So we also captured LIBS spectra in extreme ultraviolet range. Of course, when we use such region, the plasma right sustaining time is quite small, and the size of the plasma is also very, very small. So it was not so easy to capture the spectra, sulfur spectra in vacuum condition. However, with using helium ambience, we could see the improvement in the optical emission lines of various such copper as well as sulfur emission lines. Very distinct emission lines were captured, and it clearly showed that how the clearly showed that copper and sulfur diffusion is significantly increasing with the aging effect. And we also did the laser in LIBS technique, we used this as a for scanning the whole press board, right, across. And in this case, we used a failed press board insulation material, and we tried to capture the information related to the diffusion of copper at different points. What we could see here with the color diagram, that how the corresponding emission intensity of the copper emission lines are changing. So we can see that there are some regions in and around such defects over here where copper concentrations are quite large. That's what was captured over here in this colored right representation. So spatial distribution of copper was also studied in this. Now I will quickly give you idea that we also used the same approach, pulse laser deposition, while pulse laser assisting of assisted micro-scribing. Yeah. Do I have still 5 more minutes, right?
Yes, you can.
Do I have?
Yes.
Yeah. Okay. So. Yeah, so we use pulse laser microscribing approach for certain applications, particularly in order to develop some patch antennas which can be used for various electromagnetic radiation measurements, etc. So those antennas are made from copper deposited on some composite materials, and we wanted to see whether we can use such LIBS technique in order to measure the depth that we are reaching while we are scribing this copper films deposited on the composite materials such as polyamide or some other fiber reinforced material, etc. So this technique is basically the same approach of LIBS, where we use laser, but here the laser which is used here is for scribing the copper film, and when the scribing process is on, we will try to capture the optical emissions from the plasma which is generated during the scribing process, and that optical emissions, which is nothing but the LIBS spectra, can indicate the presence of copper, or basically or the depth that we can achieve. So we wanted to see depth calibration of this copper while the scribing process is on, and whether we can achieve that or not was the idea. So this is just one view graph which shows how the laser ablated film looks like when we do line scribing, right, and we can see that this copper film is getting ablated over here. This region, what you see, the red region, is nothing but the redeposit region, the material which is getting ablated or recast region to certain extent, right, or it forms a crater, right, which is the region. And this part is the texture of this laser scribed region, which shows right of the order of means sub-micron level the surface roughness that can be captured. Now coming back to our idea of how we can use LIBS. So this is the LIBS spectra obtained on the copper thin film deposited on such polyamide surface, and we can see that when laser ablation starts, we will be able to see right very distinct right characteristics of copper emission lines which were used in order to determine the depth of progression of the scribing process. And when we reach to the point where we end up in the substrate, we could see that aluminum, calcium, silicon, all that substrate related optical emission elemental lines were captured along with the copper emission. However, the copper intensity had reduced significantly from this optical emissions with the copper film, and so that was the first part. and in the second part we could to certain extent we could calibrate and we could see that with increasing number of scans how the laser intensity is decreasing, and correspondingly how are we capturing the depth what we are traversing through. So there was right, we have to calibrate with the corresponding depth that which we are achieving using optical profilometry, and then correspondingly what is the LIBS emission, optical emission intensity. And when we reach to a particular point in the dielectric, we will end up with right ablation of this material, right. So this technique certainly doesn't give exact position where we will reach to this copper thin film only, because there are so many other thermal aspects etc which will in spite of laser ablating only the copper film may also affect the dielectric. So basically our intention is go up to certain position using laser ablation, direct laser ablation. However, subsequent micro manufacturing of such scribed micro-scribing is will be done under certain other medium which will allow simultaneous etching when the laser ablation is taking place, and that too we are using a salt solution, so that laser ablation along with the salt solution provides a selective etching of copper film alone when we reached very nearer to the region where the ablation means the scribing depth is achieved. So this is our idea. So we are trying to extend the approach of laser scribing towards achieving only the copper material removal, and LIBS was used in order to study how can we understand or characterize the depth what we are achieving. This is my last part of my presentation. This is somewhat related to how can we carry forward our laser ablation LIBS approach towards online coal characterization. So certainly coal characterization is many attempts have been made in order to ablate the coal and measure certain species related to maybe S elements or related to carbon etc. And sometimes researchers have also attempted to work on determining the fly ash related elements etc using such LIBS approach. What we focused in this study is whether we can do time resolved LIBS analysis of coal to determine carbon concentration using molecular carbon emission. So our approach was over here is more focused towards try to achieve or try to obtain or observe carbon emissions very clearly, distinctly, and so that we can account for all those emission lines in our estimation right of the carbon from the coal right during ablation. And then if we can correlate it with the actual percentage of the carbon which is being measured using some other right techniques, so such as inductive ICP, OES etc. So we studied this quantification basically by using LIBS technique, and we made use of basically all this elemental lines present in this carbon coal ablation related to carbon, related to ash etc. At the same time what we did is we also focused on how to improve the carbon emission lines, because when we do the laser ablation in air, the carbon which is being emitted, which is being which will emitted from this coal carbon atoms etc. will react with the surrounding atmosphere, will also form some other compounds etc. So we will not be able to track the real carbon which is getting ablated from here. In order to track this, can we use a particular ambience? So of course vacuum might be a very good idea, but then it's not a good solution in online measurements. So the approach should be, if we can do online measurement at the same time, try to capture the carbon information. So what we did is we studied this approach with the help of different flow of gas from the nozzle attached near to the ablation zone, which will provide some surrounding getting properly controlled in terms of the ambience will be taken care with the help of either helium or argon, etc. We studied this in the presence of air, nitrogen, no flow of air, any medium, or only ambient air, helium, etc. And we tried to study various optical emission lines in the UV region partially and in the visible region. And from those optical emission lines, we found a very interesting outcome that argon atmosphere near laser ablation improves the spectral emission characteristics. Of course, it is related to the argon interaction with the laser ablation process, as well as allowing carbon or protecting carbon from the ambience as well as nitrogen, so that it should not get into some other molecular signature. And we used basically we also found that in case of argon, the plasma growth is substantial, because the effect of the E by M ratio, basically it is nothing but the electron energy versus atomic weight ratio provides. If it is small, automatically it will provide better plasma growth, and that plasma growth improved the optical emission lines, distinct lines of carbon, as well as we could also observe very distinct C2 bands, etc., corresponding to the carbon emissions. Why? Because now the carbon was interacting within its plasma with its own carbon molecule atoms, or the atoms which are emitted or nitrogen atoms, etc., which are generated during from the coal itself. So this technique helped us to first of all separate this carbon emission lines distinctly. Secondly, we also, as I written in the beginning, time resolved studies were made in order to capture the optical emission time, plasma persistence time corresponding to the carbon emissions lines around 248 nanometer or so, and those optical emission lines were used in order to capture more information about the presence of carbon. So from the lifetime of this optical emissions, and this is we have plotted a calibration curve for reference carbon weight percentage versus the C2 persistence time. What we found that within a certain small region of this 30 to 70% carbon, the emission line seems to be somewhat linear, and using this linear emission plot and coupling it with the spectral characteristics of this carbon as well as S elements, etc., we plotted the calibration line by combining optical temporal characteristics with the spectral characteristics. And then when we saw that the calibration curve characteristics was quite, it improved a lot as compared to what you can see here, as the reference carbon percentage, which was captured using ICP-OS various by other technique. And this carbon percentage from the coal sample was matching with what we predicted using what we calibrated using our spectral and temporal characteristics. We also took some samples and predicted its right carbon percentage, and we could measure such out characteristics with the right error within the range, with the spectral and temporal data within the range of few percentage, right, with respect to relative standard deviation or root mean square error value. So, and this variation over here, which is shown in terms of error bars, also is attributed to the homogeneity, right, of the coal sample itself. So that also varies from point to point. Hence, while doing the laser ablation with a rotating target, we will never get right. We will have some error bars, but that error bar was also very much within the control, and the homogeneity also could be captured. So, in conclusion, the applications of LIBS, we have tried with wind turbine blade structures, basically to develop the technique to measure the surface pollutant, and remote sensing using LIBS approach, solid insulation in transformer, and then LIBS combined with micro-scribing. The challenges are real-time calibration approaches, and how about powder LIBS? When we are working with powder, powder gets blown off. How can we capture the LIBS spectra? So this I will skip, but the LIBS has lots of applications, and this is thank you very much for your kind attention, and these are some of our researcher team members who have worked with us for developing such techniques. Thank you very much.
Okay, thank you very much, the Professor Nilesh Vasa. It was very, very interesting.
So when using LIBS, how to distinguish the noise from the elements ablation of the optical imagery of plasma bloom or optical plasma emission feeding the spectrometer. So basically delay time, appropriate delay time helps us to distinguish continuum and the characteristic plasma emissions, one aspect. And secondly, the spectrometer helps us to distinguish this optical emission depending upon the elemental right emission specific characteristic lines. So that is the one which helps us to distinguish. Now the noise from element ablation, in the sense that basically we consider that is nothing but the continuum initial noise. So it's the delay which helps us. So generally we keep a delay of 1 to 2 microsecond from the point of laser ablation in all cases. So would the use of LIBS on high voltage conductor cause field enhancement on the electrical field via altering the geometry, or would the changes be negligible? So of course we have not studied in such a way, but basically our study was focused on, most of the time our studies are focused on right. So in case of let's say in case of transformer etc., when we performed the LIBS, it was on insulation material, right, directly. So which didn't affect right, because the plasma which is generated is of the order of few hundreds of micrometer size or even less. So that we have not studied its its influence on the electrical field etc., but we do not expect it to be so significant.
So thank you very much again.